In this video, we're going to derive an equation for impulse. So let's start with a situation where we have our two cars and the two cars are traveling towards each other and they collide with each other. So I'm going to put car 2 here in my system and I'm going to draw a force diagram for car 2. So we have force of gravity acting down on car 2, we have the normal force acting up on car 2, and then we have a force applied, and this is force from 1 on 2, and that's in the positive direction. So I'm going to say sum of my forces in the x direction on car 2 is equal to just this force from car 1. And I know that the sum of my forces is mass times acceleration in the x direction, and I know that this is force from 1. I also know that acceleration is equal to v final minus v initial over t. So now I'm going to plug that into here, and I get mass times v final minus v initial over t equals force 1, force applied. I'm also going to put a delta t here. We've been using t and delta t interchangeably in kinematics. Delta t is usually used in this situation, so we're going to use delta t. I'm going to multiply each side by delta t, so we have mass times, and I'm going to distribute my mass. So mass times v minus mass times v initial, and that is equal to my force applied times my change in time. Now I also know that mass times velocity is equal to momentum. So this term right here is initial or final momentum. This term is initial momentum, and I can rewrite this as, I can rewrite it several different ways, but we can write it as final momentum minus initial momentum equals force times change in time. I'm going to drop the delta t, or the little 1, so that's just to make it more general, force times change in time. So I have an equation, and we can write it a bunch of different ways. So a delta p, which is change in momentum, that's equal to mass times change in velocity, which is what we have up here. This is mass times change in velocity. And that's equal to force times change in time. And that's all equal to something we call impulse, which is, the symbol for it is a J. So this is impulse. And I have a little slide later that shows you the symbols and the units and all that stuff. But impulse is just a special name for change in momentum. And it has two different equations. So it's mass times change in velocity, or it's force times change in time. So I'm going to skip around a little bit here to this slide right here. So this is data collected from a ball bouncing off a wall. So I mounted a force plate to a wall, and the force plate recorded the force as the ball was bouncing. And it was a little bit of a squishy ball, so you can see the ball kind of squished quite a bit as it was bouncing off. And the force plate, so the force plate's mounted to the wall, and it measures force versus time. And then I also had a motion detector like in front of the ball, and the motion detector detected the velocity. It's kind of like a little radar gun, but it graphs the velocity. So it detected the velocity of the ball before, during, and after the collision. So if we look at the velocity versus time graph, this is when it's thrown, and then this little part here, it's traveling right before it hits the wall, and then here it's hitting the wall and bouncing off of the wall, and then here it's traveling away from the wall, and then that's where it's caught. So we can use this data to figure out the impulse with two different methods. Now let's think about how we're going to find impulse from a force versus time graph. If we think about this, we have a force versus time graph. We get information from a force versus time graph, or from any graph, excuse me. There are several things we can get information from. We can use the slope, we can use the area under the curve, or we can use the y-intercept. Those are the main things. So if you think about force versus time, in this class we're using algebra as our math, so we're just going to be using constant forces. So we have a constant force and time, and we need to think about how we would find impulse. Well, in order to find impulse, we know that we need force times change in time. So the area under the curve is going to be equal to impulse. So J equals force times change in time. Now this will get a little bit more complicated when you study it with calculus, but for right now with algebra, we're just going to do force times change in time as our equation. We're going to have constant forces. So now we go back to here. You can see that this is not a constant force. When the ball first starts to hit, the force is small, and then it gets largest like right as the ball is changing direction, and then the force decreases again as the ball starts to spring back to its normal position, or normal shape, I guess I should say. So we can use the computer to find the area under this curve. You're not going to have to do that mathematically until you get to calculus-based physics, but you can have the computer do it for you. It's called an integral, and that number right there, which is hard to see, is 1.158 Newton seconds, which is the unit for impulse. We'll talk more about that in a second. So that's the area under the curve. The other way to find impulse is to do mass times change in velocity. Excuse me. So the mass of my ball is 1.01 kilograms. And the initial velocity here, so we do final velocity minus initial velocity. So my final velocity is this right here. I've used my tool and just kind of screenshotted. So the velocity right there is 0.516, so that's my initial velocity. And then my velocity right here is negative 0.610, so I'm subtracting my initial velocity, which is a negative, so I'm subtracting a negative, so I add, and then I multiply by the mass, and I get 1.137 Newton seconds. So we can see with experimental values that my mass times change in velocity is the same, or very, very close, with a little bit of error in there, as my area under the force versus time graph. So another thing that's important with this, we're going to start with Newton's third law. If we think about this collision again with the two cars, we know that if we follow Newton's first law, the force from 1 on 2 is equal to the negative of the force on 2, or from 2 on 1. So then I'm going to replace this with mass 2 times acceleration 2 is equal to mass 1 times acceleration 1. And once again, our acceleration is equal to our change in velocity over change in time, which is, I'm just going to leave it like that instead of v final minus v initial. So I'm going to plug that in for both of those. So we get mass 2 times change in velocity of 2 over delta t equals mass 1 times change in velocity of 1 over delta t. And then you can see that our delta t's are going to cancel out. So we get mass 2 times change in velocity of 2 equals mass 1 times change in velocity of 1. Negative. I lost my negative sign. My goodness. This is negative, this is negative, this is negative. So my negative sign I lost it. Did you see that I lost my negative sign? Hopefully you were thinking critically about what I was saying and you saw that. All right, so now what this means is this is change in momentum, right? So change in momentum of 2 is equal to negative change in momentum of 1. And this is always going to be the case when two things interact, because this is just derived from Newton's third law. And we know that any two objects that interact are going to follow Newton's third law. They're going to put equal forces on each other, equal magnitudes, opposite in direction. So as long as they're an isolated system and there aren't other things going on and we're just thinking about the forces that they're putting on each other, then we're going to have the change in momentum of one of the objects is going to be the same magnitude in the opposite direction as the change in momentum of the other object. So I've kind of summed all of this up on one page here. Momentum, you should know this from reading, the symbol is a P, and I did not add my little vectors, which are hard to type, so I've just been writing them. I kind of wanted black, so why am I blue? I don't know. Okay, so symbol is P. P is equal to mass times velocity, so momentum is equal to mass times velocity. The unit is a Newton times a second, or a kilogram meter per second. They're the same thing. We know they're the same thing because, let me just show you that real fast. A Newton is equal to a kilogram times a meter over a second squared. If you don't have that memorized yet, you need to memorize that. So when you take a Newton times a second, you have kilogram meter per second squared, and you multiply by seconds, and the 1 second cancels, and you get kilogram meter per second. So that's the unit. You can write it either way, and it's kind of handy because the kilogram meter per second comes from the mass times velocity. Mass is measured in kilograms, velocity is measured in meters per second. The Newton seconds comes from the force times change in time thing, so force and time. Also, momentum is a vector. Impulse is the change in momentum. It's just a special name for change in momentum, which makes it kind of confusing. You know, we don't have a special name for change in time. We don't have a special name for change in velocity, but we do have a special name for change in momentum. The symbol is J, a capital J, and we have a kind of long equation for it because you can write it a bunch of different ways. Impulse is force times change in time. It's also equal to mass times change in velocity, and it's we can write it as change in momentum delta P. So you can write it any of those ways, any combination. The unit is the same as the unit for momentum because it's just the change in momentum, just like the unit for change in time is the same as the unit of time, and it is a vector. Also, this important statement down here that we just showed with Newton's third law, when two objects interact, the change in momentum of one is equal to the negative of the change in momentum of the other. So the same magnitude but opposite direction, and that's just derived from Newton's third law. That's all.